Hey everyone, this is the 5th summer limits video. This one focuses on finding limits algebraically using conjugates. Now some of you might not have seen this before, and those of you who did see it with me, you might need a quick review on it. So let's see what this looks like. You have several examples like this in your summer review packet. I'm actually going to do number 21 with you on the very last section of the summer packet. I think it's the last page or the second to last page. It's very, very similar to number 22. So hopefully after watching this, you'll be able to successfully do number 22 here. Notice what happens if I try to use direct substitution, which is always the first thing that I should do. So I'm plugging 9 in for every x, and I end up with 0 over 0. So this does not mean that there's a vertical asymptote there. This means that there is a hole in the function. Now some of you might be wondering, how am I going to factor the numerator and the denominator and cancel? I'm going to show you how to do that after I show you conjugates. Conjugates is more commonly used to fix this problem. What you need to remember is that the conjugate of an expression is the same exact thing as the original expression. It just has an opposite sign in the middle. So in math, it's not proper to have a square root in the denominator. And in addition, the square root is what's causing us to get a 0 in the denominator. So what we're going to do is, conjugates are used widely in many different types of algebra. It's also used in complex numbers when you use the complex conjugate. In this case, we're going to use the conjugate. And notice it's the same exact thing as what I started with, but it has the opposite sign. So it's root x plus 3. And I'm going to multiply the top and the bottom by that. Now, I see why it's useful to do that, because by making these signs the opposite, what's automatically going to happen whenever I FOIL here is that the middle terms will cancel. That's why we made the signs the opposite. So I'm going to show all the work out here. You don't need to show all the work out when you FOIL the denominator, though, in the future. Root x times root x is x. Root x times 3 is plus 3 root x. Negative 3 times root x is minus 3 root x. And negative 3 times 3 is minus 9. So very conveniently, plus root 3x minus, or plus 3 root x minus 3 root x cancels. That was the whole point, because now the square root's gone in the denominator. In the numerator, I have x minus 9 times root x plus 3. And I'm going to hold off on even trying to FOIL that, just to take a look at what I'm even left with. So I have x minus 9 times root x plus 3 all over x minus 9. And look, x minus 9 cancels. So there is the cancelant in the numerator and denominator that we are used to whenever we have the indeterminate form 0 over 0. So now I can successfully do the limit as x approaches 9 of root x plus 3, because that's all that's left. So now I'm actually going to do direct substitution. I have root 9 plus 3, which is 3 plus 3, which is 6. So the overall limit as x approaches 9 of my function is 6. So my y value is tending towards 6. However, we can probably assume it's not going to reach 6 because there's actually a hole there. Now, the way that you could, from the very beginning, use factoring to do this is by using a difference of 2 squares. The thing is, you're kind of going to have to force it. It doesn't look like a difference of 2 squares, but we can force it to be 1. So let's look at our numerator. Now, normally for a difference of 2 squares, you're used to differences of 2 squares when you have, say, x squared minus 4. And you take the square root of the first term, x squared. You take the square root of the second term, which is 2, and you do plus or minus. However, you can also do it if the first term isn't squared. So let's take a look at x minus 9. I'm going to do the square root of the first term, which is x. And the square root of x is just square root of x. I'm going to take the square root of the second term, 9, which is 3. For a difference of 2 squares, we always do plus or minus. And that's how you can force a difference of 2 squares for something that might not really look like a difference of 2 squares. And that works out very nicely, because now root x minus 3 cancels. And it looks exactly the same as before because we end up with the same exact thing we got here. It's just in this case we didn't really multiply, or we didn't multiply by the conjugate at all. We used a factoring. And you would end up again with root 9 plus 3, which is 6.